Are
Hey,
you there,
guy.
Guy?
Someone asked if this presentation is being recorded, but I see that it is. Sorry about that.
Apologies.
Hey, Guy, I think we lost you for now. Can you hear us?
Okay, I know what happened. I think somebody hit recording, or maybe I.
That
and
was
it,
me, Guy.
and it makes me to have to hit OK. So sorry.
Do you mind going over that last slide? And my apologies. I didn't mean to throw off. I just wanted to make sure it got recorded. And sorry, guys.
Which slide? This one?
The water age. Yeah.
This one?
I can't
Okay.
see your presentation.
Oh, I have to
Share.
start over again.
Thanks, guys.
I think it's this one. See this one?
Yeah, I can see it.
Okay, you want to start here?
If you could, that would be great.
Okay. All right. Start. So this is what we call a water age distribution curve. And so if we took a profile of the water exiting the reactor, we can take these, in theory, we can take the water and break it down to water elements. And each water elements represent a certain percent volume of the total water leaving the reactor and water in a certain age as well. And so each of these elements has a certain water age and also represents a certain percent volume. So as you add these up, in this case, for this graph, we get 10% at this time, which is happened to be 62 minutes. And so it's 10% of the water that exit the reactor has a water age of 62 minutes or less. And then the rest, which would be 90% of the water, has a water age of 62 minutes all the way up to 280 minutes. And what I said earlier is that you may wonder why we use 10%, versus say 5% or 15% or 20, is that EPA just came up with a value of using 10%. So they want to ensure that at least 90% of the water has a certain, disinfectant exposure time or water age. And so that's how that came about. Now, how do we calculate the bathing factor? Is that we determine the exposure time or T10 value from the tracer study. And then part of the tracer study is that we determine what the hydraulic residence time is, which is the operating volume of that clear well divided by the flow that's coming out of the clear well. So, and we get a time, what we call hydraulic residence time. And the balancing factor is simply the disinfectant exposure time from the tracer study divided by the hydraulic residence time. And that value is going to be somewhere between 0 and 1. It won't be 0, and it's likely never going to be exactly 1. It could be close to 1 if it was a pipeline, a very long pipeline. And that baffling factor is what we use during our daily CT calculations that you use in the, for your surface water plant. It's applied daily to the plant's clear well operations based on what the flow leaving the reactor or the clear well, what the tank level is, and so forth. And so that bathing factor is applied to calculate what we call the exposure contact time. And then the next concept is, what is CT? And CT, I call it the delivered disinfection dose to the pathogen. it is, the C is the disinfection residual measure at the designated sampling point, which usually it's going to be after the clear well before the first customer. And the disinfection exposure time is that, or contact time is the sample point of the measure disinfection residual. So wherever you measure chlorine residual, that's also your contact time as well. And to determine the T10, we take the baffling factor from the tracer study, multiplied by the hydraulic residence time, and that will give us our daily T10. And from that, we calculate taking the chlorine residual and the T10, we get our what we call our CT value, and that tells us how much, by looking at a table or using a calculator, we can determine how much log inactivation we're getting daily for Giardia cysts. All right, so let's go over some types of tracer methods. There's one, the first one's called a slug dose, the pulse input method. And this is basically taking the tracer and just adding it all at one time before the clear well. And the test for this takes anywhere from what we call 3 to 4 times the hydraulic residence time. So, for example, if that hydraulic residence time was 2 hours, then the test would be 2 hours times 3 to 4 times that would be 6 to 8 hours to run that test. And then we have what we call the step dose method, which is just a continuous tracer feed added throughout the test. And the same thing, the test duration is anywhere from 3 to 4 hydraulic residence time. And the reason for this 3 to 4 hydraulic residence time is that, like for the slug dose, to get complete, whatever you're adding, to get complete removal or recovery of that tracer, you need to run that test for 3 to 4 hydraulic residence time. And the same thing for the step dose. Before to get to see steady state, it takes about 3 to 4 times the hydraulic residence time. And then a third test that I developed years ago is what I call the modified step dose method. It's like the step dose, which is a continuous tracer feed added throughout the test, but the test duration is less than 1 hydraulic residence time. And this is the method that we'll be using for Bass Lake next week. Now, what the curves look like for the slug dose and step dose look like this, what you see. So on the left, you see a curve that goes up to the, peaks out and then slowly comes back down, decays back down. And then a step dose is a continuous feed tracer where it's slowly going up and then finally plateaus. And the x-axis is normalized the time, so it's basically the measure value divided by the hydraulic residence time. So you see I have 3 residence. At 3 here, it takes, for the slug dose to completely go back to background. And for this graph on the right, for the step dose, it takes about 3 to get to steady state. So let me give you an example of a couple studies using the slug and the step dose. Here's a kind of a unique clear well. It's basically it's a horizontal vessel with baffles, and the water comes in here, and it has portholes here where the water comes in. And this is a 20,000 gallon tank, and it flows 210 gallons. Now, can anybody see, like, from this design, any issues with this particular design? Any thoughts that you may have on this? So
I didn't
go
see
ahead.
the notched baffle. Anyway, it looks like it'll move through the center of the line pretty readily, but I don't.
Like this?
Yes.
Like this? Yeah.
Yeah.
Yeah, that's how I'm thinking, is that the velocity is very slow velocity, so there's no really mixing going on. And I'm thinking the water is going to come in like this and then come out. What I would done is that extended these baffles all the way, not all the way to the end, but pretty close to that, so that it'll force the water to go serpentine up and down versus just going through here. This particular system, this design, the manufacturer thought the baffling factor should be around 0.7, and which wouldn't achieve that based on just looking at this. And so this is what the vessel looked like, and this is what the curve looked like. This is a slug dose, and it ended up being a 0.45 baffling factor. The hydraulic residence time is 95 minutes, and so I carried out the study up to 280 minutes. And then here's the system we did in Fresno. It's an ozone contactor. This is the underground system ozone contactor, which they're one on top of the other, and the water flows in and serpentines around this baffle, and then it flows up to the next baffle, comes out here and around and out here, and this is where we're taking samples. So the main thing I wanted to show is that if you look at the hydraulic residence time, it's only 16 minutes, but here's the curve, what it looks like. You get a nice curve like this, and out like that. And so we're doing the frequency of sampling is pretty intense. It might be every, 20 seconds or something like that for this kind of reactor. But what happens if the hydraulic residence time is really long, like several hours, where it's not practical to, run a test for 8 to 12 to 24 hours. And, also plants, like your smaller plants, they don't run 24/7, or, they may only run 3-4 hours a day and they're shut off, or they might run 8 hours, but during that process, they have to do backwash or something else going on. And so this is how we kind of develop what we call the modified step dose, is that the test is complete less than 1 hour. And the measurements that we have is that we were taking samples going into the inlet of the clear well and samples going out. And so we have a tracer here. We're pumping like a steady state into the pipeline. And then we're measuring we're taking samples here so we can actually know exactly what we're dosing into this clear well. And then we'll take samples on the outlet. So here's an example of a system we did a few years ago, where it's a clear well, where we're adding the tracer here, we have the treatment plant, and then we're monitoring, we're taking samples out here before the clear well. And here's the inlet, outlet here. I think the inlet's at the top, outlet's at the bottom, pretty close, and they have floating surface water aeration system with a mixer. And then the water's being pumped out. And so we take samples on the inlet, and these are the actual results of the tracer dose. So now we know what the dose is. And so one of the advantages of doing this method is that we don't have to worry so much about whether the feed pump is pumping what we thought it was pumping, or the solution strength is what we think it is. Solution strength might be a little bit weaker than we think it is, or stronger, or the pump might be pumping less than what we think it is. All that really doesn't matter because we're measuring the actual, residual of the tracer that's actually going into the storage tank. And then the graph is going to look like this for a step dose, for the modified step dose curve. It's just going to be points going up. We're never going to hit, steady state because we're shutting off. We're doing a study that's less than 1 hydraulic residence time. So for this one, the hydraulic residence time was almost 5 hours. And we did this test probably within if you look, just a little bit over an hour, So here's a test that we complete just within an hour. And we did the step dose. We're talking 15 to 20 hours just to do a step dose, if you went out to steady state or if you did a slug dose. So this is kind of the advantage where we can be done pretty quickly and have very accurate results as well. So is there any question before I start with the Bass Lake?
I have a question, Guy.
Sure.
Just in your experience, how often is a tracer study required for new clear wells?
It's going to be district dependent. So,
Right,
every
in your district, how
uh,
frequently is it?
we don't have any, maybe Cindy can ask, chime in, but it's not too many clear wells that go in all the time. So, if there's something that's seemed to be interesting to do, we'll do it, because we're local here. So if not, what we will do is if it's something that uh, that's similar to studies we've done before, we can assign a baffling factor, that's more conservative than what it may achieve. So, it depends,
Yeah, agreed, Guy. If Guy has this extraordinary database of all these different design configurations, and a lot of our district, if a clear well does go in and we think they can meet it under certain design parameters, they'll usually just do that. But yeah, but if it's different, then we'll recommend a tracer study.
Yeah. So, yeah, I mean, the more studies we have a different configuration, the more, better our database is, so that we can do, prediction and so forth. And then Bruce, you have a question?
Yeah, or basically I just was trying to double check too, or not to doubt this, but regardless of the method, somehow between the three tracer methods available, they've kind of been cross-checked, or they all end up with similar results.
They should. I mean, I've
You
probably
know what
done
I'm
more
saying?
tracer stuff. Yeah, I've done that. Like when I first started to modify, I know it makes all sense and all that, but I just to show like somebody that doesn't not doesn't have a lot of experience. I've done tests where okay, we did a step dose, the full step dose, and then we did a modify, and we basically get the same results. So, uh, yeah, it's so this is something I've been doing for started to modify. I don't know, probably close to 20 years ago. So, after I've done so many tests, it's like doing the step dose because when you first do this, you're only introduced your knowledge is kind of based on what you read about, like the step dose and slug dose. But then as you start doing these studies, you start to learn and become, and you learn, and then you say, well, what can we do to make this quicker? Because there's, like I said, there's uh, tanks you just can't go for 24 hours, right? And you'll see consultants, they'll do that. They'll say, well, we got to go for 24 hours to get the steady state, which they could have done in maybe in 2 hours. And so the way I have this set up is that to do the modified step dose, you have to measure what's going in to verify what you're dosing. With the step dose, let me go to step dose. The step dose is that they're using the steady state to determine what they're dosing. So they might think they're dosing at so many, say 2 milligrams per liter, but is it 2 milligrams per liter when they actually got steady state? It might be 1.8, and they'll use that value, or 2.2. And part of that is because they're not measuring what's going into the tank. They're just waiting until they get to steady state, which could be, several hours before they reach that. With my method is that we're measuring what's going into the tank, so we know what we're dosing. So we kind of any issues with the chemical feed pump not pumping what we thought it was pumping, or the solution strength, that all goes out. We don't care about it anymore because now we're measuring what actually is going into the tank. So we use that dose and then if we're dosing 2 here, then we're looking for 0.2 coming out here, which is 10% of that. So any other questions or thoughts you may have?
Guy, in terms of on rare occasions you have tanks with piping to bypass and some valves. Will the slug dose method be the only method that really could capture something like that event is occurring, or could the step dose see it at steady state if it's significantly different from what the anticipated steady state? I'm just curious your thoughts on that.
Yeah. So Cindy was saying if this had a bypass here, you would do your tracer study, but what would happen is, say some of this water being bypassed, and we had this happen once, and I was able to finally. Well, let me back up a little bit. Let's say you had a bypass, you'll still get your 10%, but that may come later, and so somebody that's not experienced, they might think, the results are fine. But somebody with a lot of experience, they might say, well, wait a minute, that doesn't make sense. This baffling factor should have been in the range of here, but now it's like, instead of being like point, say for this tank, maybe instead of being 0.4, it's like 0.7. So if I get a 0.7 out of here, that might mean that maybe we got a bypass here because some of this water is going this way, and it's not, it's so, you only have half this much water going in this tank. And so years ago, we had a tank where they had a bypass, and we did a step dose. And looking at the results, it didn't make sense. And so I kept asking the operator, do you have a bypass? No. And they finally said, yeah, we have one, but it's been closed. I said, can you check? I said, it's closed. And after few times calling him back, I said, go check it and make sure it's closed. He found the valve was open. So they had a bypass going on. So if you did a slug dose, you would never see, on a slug dose, if you had a bypass, you would never see 100% recovery. You might see, it'd be something way less than that. So that would, that's something that a slug dose, you would see something like that if you had a bypass. So, I mean, you could, I think with this modified step dose, you would know that if there's something, it was something wrong, because the baffling factor wouldn't be in the range where it should be. So let's get down. Any other questions on this? Okay. So this is the Bass Lake Clear Well. It's a almost 70,000 gallon tank. It has 3 baffles. And the inlet is configured such that it has a pipe that comes in and 3 outlets, one here, here, and here. And then the outlet is the same configuration where it's at the bottom, midpoint, and top. So I think this is halfway, like 8 feet. This is 16 feet. And this might be a couple feet off the ground here. So the test we're going to run at, the flow is 300 gallons per minute. This is at the lower flow, like I'm thinking like winter flow. It's going to be a lot more conservative versus running at 600 gallons a minute. When you have baffle tanks, the higher the flow, the more mixing you'll get, the better baffling factor. So the low flow should be the most conservative. Now they're going to be running to waste, not to the distribution system. So this pump will not be on. It will just be gravity flow through this pump, and the operator will be maintaining, and I'll have it in the next slide, they're going to maintain a certain water level. And so by maintaining a certain water level, if they're running 300 gallons a minute, then we know it's 300 gallons per minute coming out. This is what the clear well looks like here. And I have some pictures that Bruce sent me during construction. So this is without the baffles. And you notice these are a bolted steel tank. And this is one of the, I think, inlet maybe without all the piping yet constructed. And then here's another photo. And one of the things that concerns me is the bolts here. And show you in a minute here what that I'm concerned about. So here's the baffles. There's 3 baffles here. The water's going to go, serpentine around these baffles. And then here's the outlet pipe that's fully constructed. Oops. And so you have, water coming here, here, and here. And this is the same thing on the other side for the inlet. And one of the things I think is going to happen is that when the water comes in, I'm assuming this is the inlet, the water's going to come in, I think it's all going to go to the bottom. I don't, this is an 8-inch line. This is 300 gallons coming in. I don't know if you're going to see much water coming out of here or the top. I think it's all going to seem like it's going to me, go to the bottom. The other concern is the bolts here. So there's no good picture to see what it looks like under the bottom, but if you got a gap here from the bolts, you will get short circuiting under these baffles. So that's I wish that somebody had taken some pictures here so we could at least see what it looks like, at the bottom, next to these bolts here.
Hey, Guy, on that inlet, could you 90-degree it towards the
this is the outlet. Well, this is the outlet, but the inlet looks just like this. So this is 90. This is the flow for this. It's going to the back, right?
Yeah, I'm wondering the bottom one, if it could be turned towards us, the viewer.
Well, it's not it's just bottom. It just drops vertical down. What I was thinking is, let's say we do the tracer study. It's a very poor baffling factor. The system, the water, you can't go in and I think this is threaded. You can't plug this off and that off, and so the water had to be forced to go out the top. Okay. And then you do another study just to verify what that is. All right. So here's the where we're going to inject this fluorite. This is where they're adding their chlorine. Now, because they're going into waste, they don't need to add chlorine, and so we're just going to use this injection port for the fluorite. And we're just going to have a bucket, and they're just going to pump out of this bucket right into here. The inlet sampling point is going to be at this location. So what I was told, this is where a sample line for the chlorine, I believe. And so the operators will need to retrofit this with a sample tap so we can take or samples or inlet samples here. Is that right, Sean? Oh, you're muted. But
yeah, that's correct, Guy.
Yeah. So I think they just pull this hose off and just use this gate valve here, or is that all you have to do?
Yeah, it's pretty simple.
It's not, or is this a one-way valve, or can this water flow out this way? Oh, it does flow out this way.
It flows out.
Yeah. Okay.
It flows out now, right?
Yeah. And then the clear well outlet. So here's the outlet right here. Now the sample, when I went inside the building, these are booster pumps. Their sample tap is right here. So if the water is going to distribution system, it's right here. But the problem is we're not going to the distribution system. We're going to gravity that way. And so this line here is dead water. So we can't use this sample tap because there's no water flowing through here. It's just sitting here. So we go outside the building. This pipe here is right here. And this is the hose that's going to waste. And this is why I wanted to say, when talking with Clint, he thought to replace this coupler and put a sample tap on it. And as I thought about it, I don't think you're going to get any water out of it because of the flow velocity going through this pipe. It's about over 7 feet per second. And I think you're going to create a vacuum pressure here where it's just going to suck in air. And so this is something we need to figure out before next week, is that how we're going to sample out of this line here. And I don't know if you can put some kind of back pressure on here or not, but you could try putting a sample here, or maybe you stick it. I don't know where you can put one, unless you put a copper tube in there that faces, the direction of, or the opposite direction the water's flowing. like, you know what I'm talking about? Like you put it has to be something like an L.
Well,
You understand
Guy,
what I'm saying?
what I
Go
can
ahead.
do is change the valving underground, and instead of going to waste how you have it in the photograph, I can go to waste out of the fire hydrant that's in the parking lot, and we'd be able to use the sample tap in the high service pump station.
Okay. Right here, you mean?
Yeah, we'd be
Okay.
able to use that one.
Okay.
We'd send the
So
water out.
it just still be gravity then, right?
Yes.
Okay. All right. That'll work. So we can then, so somebody will need to be here with the bucket, you know, just, so when they're doing their sample, they'll just run it into a bucket and then they'll, you know, so you don't get water all over the place, and then they can just take your sample, you know, from a bottle, you know, to get their sample bottle here. All right. That'll work. Okay. So as far as our tracer solution, how much, well, we're using a hydrofluoric silicic acid. It's of that solution of that trait of that fluoride, 19% is actually fluoride. And I left 1.5 liters of the fluoride there with you. And what we're going to do is we're going to mix up, you're going to mix up the 1.5 liters to 2.5 gallons of water. And this is the bucket I left, and the fluoride, it's in a couple liter bottles inside this bucket. And what you're going to do is that you can take this bucket or your own bucket, but you're going to add first water, and then you're going to add the acid to it and mix it up. So you don't add acid and then the water. You add water first, and then you add your acid. You get that, Sean?
Yeah.
That's important. That's important. You don't want to add water to acid ever. So so you're just going to have about I think it's going to be about 2.9 gallons of solution only in a bucket. So that's all you're going to have. And then the feed pump, you're going to use you have a peristaltic metering pump, and the capacity is 24 gallons a day, and that's 63 mils per minute. And based on the flow, like plant flow is going to be 300 gallons a minute, and based on the capacity of this pump, we're going to dose about 1.78 milligrams per liter. So the feed pump operation is that you're going to set to full capacity, and then what I recommend is just verify the rate, just with just water. Just ensure that it's pumping pretty close to 63. It's not like 23 or something else, and then we need to know how long it takes to pump from the bucket to the injection line. So that line, I don't know what the size of the line you're going to use, but we didn't know if does it take 30 seconds, it takes a minute, to pump from the bucket to the injection line, because we don't want to start our timers as soon as you turn on the pump, because it takes a certain amount of there's a delay before the tracer gets from the bucket to an injection point. And so we can look at the diameter of the hose, the inner diameter of the hose, and determine how much volume that's in there. And then we can look at, how long is it going to take to pump, so we know it's 63 mils per minute. So, the hose might be, say the hose is 63 mils. So it's going to take 1 minute to pump from the bucket to injection line. Okay, the plant and tank operation is that we're going to set the plant at 300 gallons a minute, and we're going to clear level setting is going to be 19 feet. I know your max is 20, so 19 is a good number to work with. And then you're going to adjust your gate valve because it's gravity, to maintain that tank level of 19 feet. So if it's maintained at 19 feet, so we know if it's 300 going in, it's 300 going out. So that's something you might want to do beforehand. you know, so you get your valves already set. So when you do start up, you don't have to do much, you know, adjustment if you can do that before the study. The total duration is going to take, the test is going to take 1 hour and 52 minutes. So that's how long we'll be there. You'll be there doing sampling. So for the pre-tracer study instructions, we're going to operate, before we actually start adding the tracer, we want to operate the plant for 30 minutes just to get everything at steady state, hydraulic steady state through the clear well. So we want the clear well start, you know, the water in clear well to start to move and get it to steady state. And 30 minutes is usually a pretty good number to use for that. And then also, if you need to adjust your gate valves to maintain the clear well, that gives you time to do that as well. As far as alarms, MIT, you want to disable the features to ensure that there's no plant interruptions, right? We don't want to start the chemical feed pump and then after about 20 minutes, the plant shuts off for some reason because it's time to do a MIT or something like that or something else. So we want to ensure that these features are locked out so we ensure that we can run for about 2 hours without interruption. All right. Let's talk about our sample frequency. So for the outlet, you'll have I'll give you a form that has the sample intervals on it. And basically for the duration of the test, we're going to start out with 3-minute sample intervals. And we're going to sample for every 3 minutes for up to the first 42 minutes. And that's associated with a baffling factor from 0 to 0.2. And then from there, we're going to sample every 2 minutes for the rest of the test, from 42 minutes all the way to the end of the test. And it's associated with a baffling factor 0.2 to 0.5. And so this frequency is such that, you know, I think the tank should be around 0.4 or so, but if you have something going on with the curtains, you know, or the baffles where you might have leakage or anything, well, this should help capture this right here, this frequency right here. And I'm pretty doubtful that the tank will have anything really over a 0.5. So this should be plenty right here. The instructions for taking samples, that before it's time to take a sample, you want to rinse the bottle out first, at least once, before taking your samples. You want to have a phone or a stopwatch to keep track of time. Usually we're using phones, so you want to have at least 2 phones or more that we start the timer all together, because if something happened like it did with me, the last time I was doing a church study, I accidentally stopped my timer on my phone. You know, I accidentally hit the button, so I had to go to use somebody else's phone. So it's good to have a couple phones in case something happens with the timer on one of the phones. If you have any sample issues, like say you missed your interval, like you got distracted and it's like over 20 seconds has elapsed when you're supposed to take your sample, just take your sample and write down what the actual time was, the interval time was. That's all you have to do. So don't panic or anything like that. If you mix up on a bottle, like say you're on bottle 9, but you grab bottle 10, well, you can, if you have time, you can just transfer that water to bottle 9 if you have time, or you just make a note on the form that this is bottle 10 versus bottle 9, you know, or vice versa. The bottles are numbered, and we're going to do 50 bottles for the outlet. It's going to be numbered 1 to 50. And this is kind of the form I'm going to give you. It has elapsed time, bottle number, elapsed time here, and also elapsed time in minutes and seconds, and then interval. And this is the calculated baffling factor for each this time. So, you know, this is just a snapshot. So there's 50. There's 2 rows of this, but and then at 44 minutes, you just have to be aware that, and usually I have this color coded. Maybe I'll color code it for you. Where now we're at every 2 minutes. When we hit 44 minutes, and everything else is now sample every 2 minutes. So based on the tank volume, the tank level of 19 minutes or 19 feet, the volume is 62,700 gallons. And using an exit flow of 300 gallons a minute, our hydraulic residence time is 209 minutes. So our sample frequency is that, I will increase the sample frequency during the range where the baffling factor might fall into. And so I'm pretty conservative here, or liberal. I don't know if we call it conservative, liberal, but I'm going from, I'm assuming it goes somewhere between 0.2 and 0.54. And the sample frequency, what I call critical sample frequency, is based on the nearest decimal point of the baffling factor that I want to achieve times the hydraulic residence time. So let's say I want to be able to have a decimal point, to the nearest 0.01 for baffling factor. I just times that by the hydraulic residence time, which is 209 minutes. That gives me 2 minutes and 9 seconds. So we don't want to sample every 2 minutes and 9 seconds, right? We want to have some even numbers. So we'll just round down to 2 minutes. And that's our frequency. That's how I come up with 2 minutes. Any questions on this slide?
Thanks for showing that, Guy. I have a question. Are the bottles at the water system? The bottles number 150?
Yes, I left the bottles there. So they're already there, just that are there with the fluoride.
And the chemical too. Okay, thank you.
Yep. And then the outlet is that we're going to use a bucket. This is kind of an example from another site. We have a bucket with the water going into this bucket. And you just try to adjust the flow where it's maybe somewhere between 0.5 to 0.8 gallons per minute. We don't need to fill up the bucket really fast, but and we want to delay the first 15 minutes because there's a period where it takes some time for steady state actually to go into the tank too. So just wait 15 minutes, and then somebody can do the bucket one, the inlet, where you start your water and just let it run. And then what you do, you'll take your bottle number, your bottle, and you just kind of dip it in, kind of swirl your hand in the bucket, just to make sure everything's kind of mixed up, and then sample. Take your sample, record the time, dump the bucket, and then start over again. And you should be doing this by every 5 to 8 minutes, taking a sample. And the bottle numbers you're going to use is from 51 to 60. So you have at least 10 bottles to do this. And that should be plenty enough to get a pretty good, of what's going on as far as what the dose is. So that's that. So the bucket is the reason we do the bucket is that in case the water, the tracer's not quite completely mixed in this line. So by running into the bucket, we'll kind of get an average of what the dose is over a period of 5 minutes or so, and so forth like that. And then analysis, we're going to assist with the analysis. Ophelia has all my instruments and instruments and standards and things like that. So she'll assist with that, and I will be collecting the bottles on my way back. I'll be coming through that area next week, and then on my way back, I'll collect everything. And if it need to, we'll have enough sample in the bottles for me to redo the analysis if necessary. And so this is the fun part where we get to see, what the results are. And it just takes this will take about an hour and a half to do all the analysis. And that is it. So do we have any questions about what you want to do for next week? And then you need to also schedule a date too, sometime next week. I will be coming through the area next Monday. But I assume you probably want to do the test either Tuesday, Wednesday, or Thursday. And that's something you need the guys work out with.
Yeah, my staff, I'm fully staffed Tuesday, Wednesdays, and Thursdays.
Okay. So Bruce and Ophelia, they need to kind of get together and decide, what's a good day to come for the tests. So the tests, hour to get there, tests are going to take a couple hours, but want to set a time so that you guys, the plant, when they get there, the plant has been running for 20 minutes or so, before you start before we actually start the tracer study. So, but you guys can work that out. And then, I'm around if you want to call me for anything, just call my cell number for any, questions you may have or concerns. So go ahead. Go ahead.
Oh, I was just gonna ask, which are the days that you said you're available fully staffed? Would you remind me again? Because I have a staff who will be helping, assisting with the sampling, and he comes into the office, or he will be in from vacation on Friday, but I need to get him up to speed on this. And so we'll see if, I'll check with him which day works for him. Anyway,
Okay,
which are the days?
Tuesday, Wednesdays, and Thursdays.
Tuesday, Wednesday, Thursday, okay.
Sean, are there any questions? Any things?
No, I think your instructions were very clear and thorough.
Okay, glad to hear. So yeah, we'll do this. There's always a hiccup. I've never done a tracer study without some kind of hiccup, but usually we can resolve it. Not a problem. But yeah. Anyhow, I'm glad I went by the plant because it's always good to go by the plant before the test. It's just to kind of see what's going on. The deal. I think the main issue was the outlet sample. Because the way it wouldn't have worked. The way they're operating as far as gravity flow. But I think Sean, if you're going to go to the hydrant, that sample tap, the faucet in the pump room will work. And so do you have I would suggest you have a 5-gallon bucket inside the pump house so you don't get water all over the place, right? You can turn on the faucet, let it go in the bucket, and then take your sample and then turn the water off. And then on the inlet, you just keep that running the whole time.
Okay.
Yeah.
Guy,
Okay.
this is Steve, and I have a question. Thank you for a very thorough presentation. Appreciate that, and I'm sure our engineer Mark Reitz would appreciate seeing it. You indicated it's being recorded. Is there a way that recording could be forwarded to him or to us so we can forward it to him so he could see? Because he wanted to be there during the actual tracer study. So it would be helpful for him to see this prior to that.
I don't think we can forward this, right, Cindy?
I'm not sure we can do it outside of the water boards. Ophelia, do you know if you're still on?
Yeah, I think you can. So after this is done, you can end the recording and then it'll take you to where the VMA or the video file is located, and you can send that through email.
Okay.
Or if it's too large, then yeah.
Yeah.
But
we are missing the first part of it, but that's fine. But the main
maybe
thing
we should
is
stop recording now.
Stop recording.
Yeah, I was worried that it was gonna. Here, I'll stop.
You can stop it for me.
Well, if you can